we've talked about mass matrices. We've also talked about integration in time for this implicit way of dealing with it. I guess that's a typo, right? Because that bracket should not be there on its own. And we said that there were two different methods of doing the integration. One was implicit, which is unconditionally stable. It will always give us an answer which kind of makes sense. It might not necessarily be correct, but it will always kind of make sense. And the other method is explicit, and that is only conditionally stable. And that means if you choose the right magnitude of the time step, if it's small enough, then you'll get a solution which is stable and may or may not be right. And so you might ask, then why would we use something that is only conditionally stable rather than one which is always guaranteed to give a solution and a stable solution? Well, the reason is that if we solve the equations explicitly, it's more efficient and faster to do, and also we actually don't have to reform the system matrices if some of the material properties change. And so there are some advantages in using explicit solutions in the cases where you think, for instance, permeability might change as a function of time or stresses or pressures within the reservoir. So that's what we'll talk about now. Okay. So go back to this. And then you'll see that there's some self-study for you to look at tonight if you so wish. And then we'll talk about stresses and mechanics tomorrow is our plan. So we've talked about one of these. So what I want to do now is I want to talk about explicit integration, compare that to implicit integration, and then use this little code we have to be able to solve these system of equations. For that, I don't think we'll get around probably to using COMSOL today. It doesn't really work very well for us, but we'll certainly use EGEFEM. So remember, go back to this. Not very clean, but you get the idea. We made this point about this figure was that we can write our equation anywhere. We can choose to write it in the future and stand at the future and use the information from the past to be able to solve for the place where we're standing now. Or we could write the equations at time t, this point here, and use it to try and project the behavior in the future. And so that's the difference between implicit, where we stand in the future and we try and use the information in the past to be able to solve for our current location in time, as opposed to explicit, where we stand at this point here and want to project into the future exactly what the time will be. We use the same relationships that describe the finite differences of change in head with time that we developed before, but this time we'll also use this expression which allows us to say something about how we can get the head at some time as a function of a change in time and a time step. So in other words, if we know what this expression is, which is this, then we could presumably substitute this here, use a time step, and add it to the previous heads, and we get the revised value at the next time step. That's basically what we're going to do. So let's try and do it. So remember, we're going to write our equation at time t. We're going to use these two expressions here to be able to project to the future, and then we're going to try and solve an expression. Same problem. So this is it. We write at the early time level with this equation. We choose to use a lumped matrix. In our previous case, the storage matrix was equal to, what was it? The storage matrix we used before was equal to 1, 2, and 1, with zeros on it. This is our lumped way of looking at it. And the utility of a matrix which is only the diagonal is that the inverse of that matrix is just equal to all the diagonal terms 1 over. So S minus 1 is equal to 1 over 1, 1 over 2, 1 over 1, zeros on the other components. And so one of the reasons to use lump matrices is it makes this inversion trivial. So we're going to use that. The reason we're going to use that is that I guess we don't have it written down here, but let's let's rewrite it. So what we're going to do is, what if we could calculate what this magnitude is here? We can define this vector. We know this head, this conductance matrix. We know this storage matrix. If we rearrange this equation 1 in terms of this, what do? We subtract this off to the left-hand side, and we divide both sides by, we multiply both sides by s minus 1, and we get this. That's all we've done to get this. So this has come to the left-hand side. We've multiplied both sides by the inverse of 1, and we end up with this. So we have a way of being able to calculate rates of change of head as a function of time. So this is just d dt of head. It's not just at one node, it's at all the nodes. And if you like, it's written at time t, this time t. So we have this. If we also use this expression to say that the head at the future is equal to the head at the earlier time, plus this is delta h over delta t times delta t, this expression here, right? So you can think about this is just delta h, this term on its own. And so if we know what this magnitude is, if we know what the rate of change of head is over a time step, which is projected to be, and we can take a time step, then we can calculate the new head. And so basically what we're going to do is we're going to define this expression, be able to substitute this into here. So what do we know everything here? We certainly know what this matrix is. We certainly know what this matrix is. We certainly know what this matrix is. And from the previous time step, we should be able to calculate what this is from the current time step we're standing. If we know all of those components, we can calculate what the rate of change of head is. If we know what the rate of change of head is, and we know a time step, and we know the previous head from the previous time step, we have everything we need to be able to update the head. If we know what the updated head is, we can go back to this and resubstitute that back in and solve for the change in the rate of change. So that's what we'll do. So the rubric is just this. We need to evaluate what the matrices are. We can evaluate the value of this from this equation 3. Once we know what this is, we can substitute the value in here and calculate what the revised head is from equation 4. And then we can go back and keep on repeating this. So that's what we need to do. And it makes the point that this is only conditionally stable, not unconditionally stable. So let's look at the system that we had before. What's it look like? We did this manipulation. You asked questions about why this has changed, but this is in its modified way. Again, we only have one degree of freedom, which is this middle node H2, because H1 and H3 are prescribed. So we don't have to change these, we don't have to change these. And so the only expression we have is, if you like, this middle equation. And so if we want to take out this middle equation, we have this term here, which I think is this. We have this term here, which is this. And we have these terms here, which are these. Oops, didn't mean to draw a line through that. And so with that, we can do what we said. We want to rearrange the equations in terms of this. So in other words, we subtract this off to the left-hand side, and we divide both sides through by storage. So that's, I think, this. This is 1 over s, which is this. This is this, and this all exist here. And this is minus kh2. And we can start putting numbers in this. Flux into the middle node minus flux out have to equal, so that's 0. The head on the top boundary is 0. This is h1. The head at node 3 at the bottom is kept at equal to 1. The term of the K matrix is 2, which is this. And the initial magnitude of this head we need to figure out. For the first time step at t equals 0 plus, h2 will be equal to 1, right? It's just this value, as it was before. And so we're able, now if we know this, we're able to calculate what the rate of change of this is. If we know what this rate of change of this is, we can put it into this expression here. Time step, we know the initial value was 1 at the first time step, just as it was here. And it calculates an updated magnitude. And that's all we're going to do. A few words about it. I guess I don't really go through the calculation. I thought there was a table here that maybe did it, but I guess not. And so for the first time step, I guess we could do the first time step if you wanted to. What's the rate of change of head? It's going to be 1 times 2. So no delta t here. So this is 1 minus 2 times 1, which is minus 1, divided by 2. So the first time is equal to, I think it's minus a half. So this expression here for the first time step will be 1 plus 0.1, which is delta t, times minus a half. And what's that going to be equal to? A half of this is 0.05, is I think this is right. That's the first time step. Let's look on the equation to see what we did before. And so first time step is 0.1. Yeah, it's exactly 0.95, right? Not a very good figure, but you see that this is the magnitude for the first time step. Incidentally, you see that on both of these figures, it goes from the maximum number of 1, and at time infinity, the value should be only 0.5. And the rationale for that is that, from what we said before, is that the steady state condition, this is 1, this is 0, the steady state condition is this, and so exactly at this point, this is going to be equal to 0.5. So it makes perfect sense that this is the lower limit of this. And so you can just step in time to solve this. So actually, that's a pretty quick derivation, I suppose. And you could write a little algorithm that would do this. I don't know if you can see this very well. I can barely see it on the bright screen. But I'll try and point out the important features. So I guess this is the curve here for time steps of 0.1 for sure. This is for delta t equals 0.1, also 0.01. They would all fall on this if you use an even smaller time step. But if you use a larger time step, then you get some interesting results. Actually, let's do the calculation for a larger time step. So what happens if we use a value of delta t of being equal to 1? So this is for delta t equals, don't have enough space. Am I able to move this over? I guess not. Oh, yeah, okay. So this is for 0.1. What if we do a calculation for 1.0? Do we get a stable value? So, does this change? This value doesn't change. Nothing in here is a function of delta t, so this will still be a minus half. If we do it for this, then initially the head is equal to 1. Delta t is equal to 1. and this will be equal to minus a half. So that's an interesting one. This is going to be equal to 0.5. So if we use a time step of 1, the first time step, it's equal to 0.5. And so plotting on that graph, you get actually this point here. So these squares on the bottom, this would be 1 second, this would be 2 seconds, this would be 3 seconds, this would be 4 seconds. So you get an interesting kind of stable result, but it's not actually the right result, but it is conditionally stable. Not sure what that is doing there, this one here. Okay, what happens if we choose a time step of 2? Then this stays the same. I'll write it down here. It starts off at 1 plus 2.0 multiplied by minus a half, which is minus 1. Minus 1 plus 1 is equal to the first time step is 0.0. And so I think that's plotted on here. You can't quite see it. Is if you use 2, the first magnitude you get is at 0, which is off the scale. This is 0.5, so it'd be down here somewhere. I think if you then do it at 4 seconds, you end up with this. If you do it at 6 seconds, you end up back down at 0 again. And then if you do it at 8 seconds, you end up with this. And so it oscillates widely between them. And so if you use too large a time step, then the problem you have is that you just get an unstable solution. This isn't so unstable. It's clearly it's wrong because it's bouncing back between these, and it can't actually have a head which is lower than the equilibrium head in the system. And if you used a larger time step, such as 10 seconds, actually, what would it be? If you use 10 seconds, what would it do? So this was 2. If we use 10 seconds, what would we get? It would be 1 plus 10 times a half minus. So that's equal to minus 4. What would it be for the next time step? I guess, yeah. So you know that you use minus 4 in here. If you plug this back into here, this would be minus 4 times minus 2, which would be plus 8, which would be 9. Half of 9 is 4.5. So the rate of change of head would be plus 4.5 now instead of minus a half. And so it would just go crazy. It would fall apart. And so the question then is, why would we ever want to use this when we can get a perfectly useful solution that's unconditionally stable? Why would we want to trade that in for something that is only conditionally stable? And the answer is, if it's not answered here, is that here we actually never have to solve the system of equations. And so we're actually never solving the system of equations. We're merely calculating with a known value of a head, known value of boundary conditions, and a known value of a storage matrix. We're multiplying it out to be able to solve for a rate of change of head. And we're using that rate of change of head to merely increment the head value from the previous one by just multiplying by a time step. And so we never physically invert the system of equations, which we do have to do when we looked at the other method. If you remember the other method, we have to actually solve it because we end up with a system of equations which looks like this, We have a conductance matrix, we have something that we want to solve for, and we have a load vector. We have to solve this by, symbolically anyway, doing this. What do we do? If you think about it, what we do is we basically multiply both sides by k star minus 1, and we multiply this side by k star minus 1. The inverse and the regular matrix just give the identity matrix, and that basically gives us h t plus delta t is equal to the inverse of this matrix multiplied by q star. And so in this particular case, we do have to invert a matrix symbolically. There are much more efficient ways to do it than inverting the matrix. We're solving a matrix. But in doing that, we're actually using much more effort than if we never do that step. So the reason for using explicit representation is that we can solve the system incrementally. We may use more time steps, but in each of those time steps, we actually don't have to keep on solving this equation. Of course, if it's a linear system and the permeabilities, hydraulic conductivities don't change, then we actually have to solve this only once and then do the back substitution. But it still takes more effort to do than doing it through explicitly. So the benefit of using explicit methods is if the properties in the system are changing as a function of time due to the pressures or the stresses in the system, and we want to be able to update them often and follow that trend in behavior. And it's more efficient to do it using an explicit method because we have to use relatively small steps anyway to be able to follow the path at which the permeability is changing. And so if we're going to use small steps anyway, we might as well use an explicit method because it's more efficient, because we never have to solve an equation, system of equations. And so that's the two contrasting ways of doing it. Yeah. The other way we could think about this is that we could also write these two expressions that we defined before. If you remember this figure we had, have I gone past it? Certainly. There it is. What we've chosen to do so far is we've written the equation at time t plus delta t for this implicit one. We've written the equation at time t for what we call explicit. And those seem perfectly logical, but we could also write the equations at any point in between them on this line, if we so chose. And so this magnitude of lambda is merely representing the fact that we could also write the equations at some intermediate place along this. And so if we do that, we mentioned before, I think it's, did I not write it out? Yeah. We mentioned before that this is when you write the equations at time t plus delta t in the future. This is when you write the equations at time t, but there's no reason why we couldn't write it at any point in between those. And it turns out that if we write them at time t plus delta t over 2, in other words, exactly in the middle of this time step, this whole time step is delta t, right, between these. T plus delta t over 2 is halfway between them. We get the so-called Crank-Nicholson expression. And so this is also unconditionally stable. These are both unconditionally stable. So this value, these two are both unconditionally stable. This is only conditionally stable. But it turns out that Crank-Nicholson is actually has a higher order accuracy than the way of writing it explicitly. And so sometimes it's a favored way of doing it. And so the way of being able to solve the system of equations in that way is just this parting shot here, this final page, and this, oh geez, yeah, is this idea. So before, what we did was we wrote these to be at time t plus delta t, but of course we could write it at some intermediate step. So this lambda is just the distance, the partial distance between these two. So in other words, if lambda is equal to 1, then what is that? Lambda is equal to 1, ht minus ht, this is delta t, then h tau is the same as h t plus delta t, and it's implicit. If I'm going to leave a gap between these, if lambda is equal to 0, then this is 0, then h tau is just equal to ht, which is explicit. And if we choose an intermediate value, say a half, we end up with Crank-Nicholson. This unconditionally stable. And so these magnitudes are unconditionally stable, and so I guess it's probably written on, yeah, it's written down at the bottom. And so this is lambda equals a half is the dividing line. This is conditionally stable. And this is, including Crank-Nicholson at 0.5, is unconditionally stable. For lambda greater than or equal to a half. It includes this. And so what you can do is then, with this, we can define what the magnitude, what the equations look like. We can define the linear gradient of head is still linear between the later time and the earlier time, so that doesn't change this expression at all. And so what we then do is we write our finite element equation at some particular value of this time tau, which is given by this expression here. And if we do that and we substitute in here, we end up with an expression like this, which we can solve, which is just a bit more involved. And we won't actually go through that. And so at the bottom of the page, it defines that. So there are a spectrum of behaviors that we can mess around with. So that's, I think, all I wanted to say about that. Let's play around with understanding how we might solve these equations using EGFM for a while. If I didn't actually set it up, but I could do it quickly, I think. It is not there. It's online if you have it. Programs. Hopefully it comes up. Yeah, great. And I'm trying to remember what I have to do now. I think not that. All right, this is what I do, I guess, hit that. All right, so let's have a look at this little bit of code. So we said before, when we look at this, the idea of this behavior is you can have a single executable code that basically goes out, and we've seen that for in these individual elements, the conductance matrices vary. If you have a 3-noded element versus a 2-noded element, probably versus a 4-noded element, right? The conductance matrices, the size of the matrix and the form of the matrix changes, but it always conforms to the same regular behavior. And the regular behavior would be that it would look, if I just use a blank page as a useful component, without belaboring the point, we know always that the conductance matrix, will look like this. And the storage matrix will look always like this. So the individual calculations for those matrices are done in these localized places within the code. And so long as we're able to have it so it generates the right form of this matrix and the right form of this matrix, then we can do that in this individual location. And so we know what the form of these matrices look like. I guess why don't we go ahead and just look at this one-dimensional element system where we know that, for instance, if we have nodes 1 and 2, then in local coordinates, the conductance matrix will be equal to this. Right? And we can think about the indexing of these numbers. And we know that the storage matrix will always look like the volume of the element, which is the area times the length, multiplied by specific storage, multiplied by this, divided by 2, right? These could be halves or 2, either way, just the easy way to write it. And so long as within this subroutine, we can both calculate the form of the conductance matrix and the storage matrix, that should be good for any particular element that looks like this. If the element looks like this, then the matrix will look a little bit different because it'll have 3 terms, but we know how to do that as well. Likewise, the storage matrix will have some different terms. What would we expect the, here's a question for you. What would we expect the lump parameter storage matrix to look like for a triangle? So we could go back to first principles, we could figure it out from this, or we could also realize that basically the storage matrix really, so we said before that this integral here is equal to the volume of the element if we add all the terms together. So if we sum all the terms together, this ends up being the volume of the element, right? So if you look at this, 1 plus 1 is 2, divided by 2 gives the volume of the element multiplied by specific storage. And so really the element is just going to look like this. And so if you wanted to calculate exactly the form of the storage matrix, I think it would look like this. So let me tell you what I think it looks like, and then we can rationalize whether that's true or not. This is thickness. Is it too low? I know it's behind your screen, isn't it? And what else? Yeah. So if you take this, the area of the triangle times its thickness is the volume. The volume multiplied by a third plus a third plus a third is the volume times 1. And so if you look at the sum of all those terms, the sum are equal to specific storage, volume times thickness, if you sum all of these terms. And so that's it. And so you don't have to go and figure out exactly what this complicated behavior is. It'll turn out to be that's the case. And so it's really very straightforward to be able to do this. If you wanted to do it for a quadrilateral element, you can probably guess exactly what it would be as well. What would it be? Storage is equal to specific storage, the area of the element, the thickness. So together these are both the volume. And you'd have 4 nodal values. And it would be, I suppose I could have written the quarter outside rather than in. It'll be that. Nothing more. So it's actually quite interesting to just to think about what these should be and rationalize why they should be the way they are. Yeah, it's symmetric. So, and really all it's saying is that a quarter of the storage is associated with this node, a quarter is associated with this node, and likewise. It's just, and so that if you draw down the head at this point, it pulls out a quarter at this particular location. So I was going to pull up EGFM, so we kind of got sidetracked. The point I was going to make is that everything's localized at the element level in a subroutine. And so if you look at the structure of this little code, and you just look at the files, then you have a main driver, and you have a library routine, and a whole bunch of input files. But the library routine means that it just changes what the form of the element subroutine is depending on the problem you want to solve. And so I think the rationale for this was that we talked last time about the numbering. So element 1, 1 is a element type 1 is for flow. Element 1, 1 is for one-dimensional flow. 1, 2 is for two-dimensional flow, the triangle element. 1, 4, I think might be for transient flow. I guess that probably is the case. Hopefully that's the case because I haven't opened this up. Let's have a look and see if that's the case. I'm not sure. Yeah, I think it is. So let's actually import it into FreeMat. So let's get rid of this. We don't need to. Let's open this. 1, 4. This is element 1, 4. Can you see that well enough? What do we have? We have inputting hydraulic conductivity. We have the cross-sectional area of the element. And now we have this capacitance. So capacitance is what we're calling S sub S, specific storage. And so in our problem that we solved, you can see here, this is the area times the modulus times the length. I guess, do we call it modulus in this particular case? Yeah, I just define it here. Yeah, actually no, I guess not. Okay, forget this. We'll go back to, I'm going to import the first one we used last time, 1, 1, because it has everything in it. It's actually 1, 1 that we need. So this is this one. Yeah, same thing. So it's roughly the same. I noticed that in the other one, the bottom part of it has modulus. So it actually doesn't make any difference in this particular case. I bet you we could run that and it would still be okay. But I think this is the one that would be better for us to do. You see that this is the conductance matrix, 1 minus 1 minus 1, 1, multiplied by cross-sectional area, hydraulic conductivity, divided by length. And this is the lump mass magnitude. Area times length is the volume. Specific storage is capacitance. And it's divided by 2. And this matrix is 1, 0, 0, 1. So it's exactly the same matrix that we have in the background here. It's this matrix here. So that exists in the same element subroutine. So what else do we need to do to be able to run this? Well, the other thing that we need, I'm going to get rid of this, just because we don't need it. Get rid of this because we don't need it. It's just cluttering things up. And we need a data file to be able to run this. So let's have a look at what the data files are. Input. I'm guessing that this is probably the right one. Let me check to see if it makes sense. How's it labeled? Input file for FEM. Okay. It's a, well, what do we have? We have 3 nodes, 2 elements, 1 degree of freedom, 2 materials. We have nodes 1, 2, and 3, which are each separated by 1 meter. We have material properties, which are they the right magnitudes? So we have, this is the element number. The hydraulic conductivity we used was equal to 1. The cross-sectional area we used was equal to 1. The capacitance we used was equal to 2, right? So yeah, so it is set up for this. This is reverberating a bit. The element associations were, if I draw it in the background, remember what it was? Well, we have it geometry was shown in this figure. So what would this be? This is element number 1 and node 1 and 2, element number 2 and local node 1 and 2. So this would be global node 2 and 3. So this would be nodes 1 and 2, and this would be nodes 2 and 3 in the data file. So let's have a look at that. Yeah, this is this here. So nodes 1 and 2, 2 and 3. What were the boundary conditions we fixed? We had a head at the top, node 1, which was equal to 0 once we started. We had a head at the bottom, which was equal to 1, which is constant. And we didn't know what the magnitude was in the middle, so it's undefined. And so this is 1 at the bottom, 0 at the top, and 0 flux in the intermediate part. So yeah, so it is exactly the subroutine that we need to be able to solve the system. So let's go back to FreeMat and import it. And so import the data file. It was this one, I think. We're going to run it. We're going to run it for this particular data file. We certainly ran it before, and well, let's try running it. See what happens. See if it runs. It did a whole bunch of stuff. So if we run it in steady state, for instance, what do we expect the result to be? So we can always think about, so this is just run it in exactly the same mode we did before. And so it seems to me, it's something I never realized until I had some of my own students working on a code comparison, that people tend to assume a lot that just because you're using a code that it will always give you the right result, and you might not have to be worried too much about checking it. But let's check exactly what this flow system is. If we have a geometry that looks like this, we can at least do this for the steady state. And this is equal to 2 meters. This area is equal to 1 meter squared. Hydraulic conductivity is equal to 1 meter per second. The head at 3 is equal to 1, and the head at 1 is equal to 0. What do we expect the flow rates to be? Well, probably easier to think about it in this kind of orientation, right? So this head of 1, head of 0, area. So we write Darcy's law. Q equals A K delta H over L. And so what is this? 1 meter squared, 1 meter per second, 1 meter divided by 2 meters is 0.5 meters cubed per second. We expect it to be coming out of this location, right? Just because of the arrangement of this. And so what do we say about positive, our sign convention? We said that in was positive, didn't we? I thought. This is Inson's question. Where's Inson gone? He's disappeared. Yeah, we talked about it when we were dealing with the storage magnitudes. Actually, was it on the piece of sheet that I was scribbling at that I deleted it? So let's not worry about the sign. But I think we said that in was positive, but I can't remember. Where are my calculations? Sorry about that. I suppose you probably can't help me too much. I need to find them myself. And so the magnitude of the flow rate would be out. So I think this would be, does this mean that Q1 is negative and Q3 would be positive, 0.5 meters cubed a second. And so I think when we ran this, I saw just in the background that that indeed was, I think, the result. Let me get rid of this. This is the bottom of the result. So we went through this. This is just steady state. The resulting magnitudes come out that we prescribed node 1 was 0. We prescribed node 3 was 1. It's calculated that the middle node is halfway between it. This is a steady state case. And it's calculated that the fluxes are equal to minus 0.5 at node 1 and plus 0.5 at node 3. So it's actually exactly what it should be. And so not only is it exactly what it should be in terms of the numbers, but I think actually the signs are the way we stated it as well, which is actually pretty cool. I'm surprised I can actually do that. All right, so that's the first part. So that's obviously steady state, and that's solving for basically a simple system, steady state. So let's now run this in transient mode. And so how do we do that? Let's see if I can remember. We probably don't need to go through all of this stuff here. It's really quite a simple system. This is the part. Yeah. So here's the part. So solve the equation of systems. Equation of systems, a system of equations. So all it does is it uses a switch that you set to some magnitude, and that defines whether you solve steady state, which is what we just did, or whether you solve it with implicit time stepping, or whether you do it explicitly. So I think we just probably have to change this. And I'm going to change it to 2 to be able to run it. And I don't know, I guess we have a time step in there. Well, let's leave that time step and see what it does. Hopefully it runs for a number of steps rather than just forever. And I'm going to do what? Does this clear it? It does clear it. I'm going to see, let's see if it works. I think it's a bit cumbersome. It doesn't write it out very nicely. But I don't know if it's instructive. I can't remember what it ultimately kicks out and whether it's worthwhile mentioning it. But let's kind of step through it. So it does some of the things we expect. It makes a conductance matrix. Yeah. It makes a conductance matrix for element 1. It makes a storage matrix for element number 1, which is this damping matrix. It puts it into the global matrix for conductance. It puts it into the global matrix for storage. And then it goes on to the second element. It calculates the conductance matrix for this, zeros them out first, and then it calculates the conductance matrix for the second element. It calculates the storage matrix for the second element, and then adds these 2 extra terms into this expression here for conductance, and the terms in here for damping. So it has that. And then it does exactly the same kinds of manipulation that we talked about before. It basically does, what will it do? It will make K star H T plus delta T equals Q star. It prescribes this, it calculates this conductance matrix, and then it solves for this vector. And it should solve and give some magnitudes which should be similar to the magnitudes that we calculated. And so the time step is 10 to the minus 4, and so utemp time. Let's see what it ends up at. I know what it's doing. It's actually doing something. Yeah, okay. Yeah, okay. It's assuming that the initial magnitudes are equal to 0. And so let's do it the other way. So what it's doing is it's doing this. So what we've prescribed is we've said that our geometry is one where we have this element that looks like this, 2 elements rather, and the initial head in this system is equal to this, 1 and 0, and then we turn this off at time 1, and it ends up going and so it goes from this point here across to here. So this starts off at 1.0. What the code is assuming, I'm absolutely certain it's assuming, is that we're starting off, we're doing the opposite of that. And so it's assuming that we're starting off at a magnitude which is this, and yeah, which is equal to 0. And at time 0, it's turning this one into this. And so the behavior that it's following, I'm pretty sure, is doing this, followed by this, followed by this, because it's assuming that the initial pressures in the system, heads are 0. And so it's changing the bottom one, it's moving over. So it's the equivalent of this, but it's kind of backwards. And so let's see. I think we can't make it do exactly what we want it to do. I suppose we could turn it upside down and do it. But they're symmetric results in some respects. And so we just did it for 10 to the minus 4 seconds. When we did it for the other case, we did it for 1 second, right? Let's change it. What do we need to change? No, we need to change this, don't we? So let's change this to this. Okay. And by the way, look, you see this is equal to, K star is equal to the conductance, 1 over delta time times the magnitude of the head, divided by, this is Q star, plus 1 over delta t times the previous magnitude. So, all right, let's see if it works. So I'm going to clear out this, and I'm going to run it, and let's see what works out. See if it works. Who knows? We always learn something every time it executes. And so what would we expect? I guess let's ask ourselves that. So I think what we'd expect is that when we did this the first time, it went down from 1 to some smaller value than 1 here. And the difference between these is some increment of head. When we do it from this, it will go up some increment of head, and that increment should be the same in any way we do it. And so let's see what that increment was. It was almost, it was 0.04, what's this? Is that right? See if it turns out to be that way. So the increment was 0.0455. Let's see what came out as. Hopefully it might be something close to that. We'll see. I've done 29 time steps. This is the first calculates the matrices. Time step is 1. No, it's different. The first time step is 0.25. Next one is 0.375. Let's see if it actually goes to the right value. It should go to 0.5, right? It shouldn't go above 0.5. And you can see it's asymptoting to that value of 0.5. So, and then stops there. So it's doing something right, or are we doing something else that we don't think is different? What was the magnitude of the storage that we had? Was it really equal to 2? Do you remember? So this initial change is actually quite large. I'm curious as to why that's the case. What's not right about this? If I look at the top, number of materials, number of dimensions, number of equations, elements. What with the the conductance matrix is 1, 1, 1, and the damping is 1, 1, 1. What is the magnitude of the values we worked with here? I guess they're the same, weren't they? Yeah, they are. So that's interesting. The lengths are the same. So, well, I'm not going to worry about it. Maybe I'll check it tonight if I have a chance as to why that's the case. It's giving a bigger time step, and for some strange reason, I'm not sure why. So if we run it in the alternate manner, I suppose at least consistently, it should give a similar solution. It runs it for 30 time steps, I guess. If we run it implicitly, what do we end up getting? We know that, for instance, if we run it at a very small time step, so 0.01, let's see what we get. I'm sure I'm doing something silly because I think it works, but I don't know exactly why it's not working. If we run it in this particular time step at the different times, it's a 100th of a second time step. It goes from 0.005 to 0.02 to, oh, did we do it for 1 second or we did it for 0.1 seconds? Before. Aha. Aha. That's why. Yes, that's why. Okay. Come on. Tell me that. Yes. All right, so let's go back. Let's not do it that way. Let's do it for this implicit method. Let's do it for 0.1 of a second. Let's clear. This is really quite a neat, I mean, FreeMat is quite a nice program, I think. Quite the fact that it's free. I don't know if, I know they charge $200 a year for a license for MATLAB for us. Okay, let's run it. Let's have a look. So what was it supposed to be? It was supposed to be 0.0455. Should be the first time step. Oh, God, so good. Isn't that good? So this is it. So it's the inverse. And so it's really just doing what we did before. The first time step is 0.0455. The second one is 0.0866, etc. And we could plot this and we'd end up with that nice curve that we had before. If we already did use a larger time step. We used a time step of 1 and it was perfectly stable, right, before, and that was fine. It gave a different result. Let's try the same time step with this explicit method, which is only conditionally stable. So we clear out this, we run it, and we see what we get. First time step is 0.05, and it should be of that order. Actually, that's exactly the exact result we got, right? And this isn't just solving this very simple equation, it's solving, you know, the proper finite element equation. We could use 10 elements if we wanted to. And I think we did it here, right, for explicitly. And our first, that's the implicit one. Our first solution as we did this was for a time step of 1, and the first value is 0.5. No, we did it for 0.1, and the first value is 0.95. So this is 0.05, right? If we subtract 1 from that, which you did for the other one. So if we do it for a value of 1, let's try that. Yeah, we can look at this instability graph. So we know, well, we don't know that. If we do it for 1, what are we going to get? Oops. Clear. So the first time step is 0.5, and you remember this one flatlined. It's just drawn here. If you did it for 1, 2, 4, 6, 8, 10. If we do it for, now if we do it for 2, let's clear it, let's run it. Again, what was it? This is the oscillating solution, I think, right? So time 1, 2, instead of being 0, it's 1. Then 4 seconds, it's 0. Then at 6 seconds, it's 1. Then at 8 seconds, it's 0. So this is the oscillating one that we have that. So I guess we're really just floating back. This is where it goes, oscillates between 1 and 0. And so the other one that we did was with 4 seconds. No, 10 seconds. So let's try 10 seconds and see what we get. It should go crazy, I think, right? And so clear it, run it. And if we go back up here, yeah, you see. So it's 10 seconds, it goes to 5, which is bigger than the condition. So it should be between 0 and 1. At 20 seconds, it goes to minus 40. At 30 seconds, it goes to 365. There's a nice number of days in a year. At 40 seconds, it goes to minus 3280. 50, it goes to plus 29,525. It's not going to take long to go out of the machine range, right? So by the time you get to the final time step, you have numbers which are 10 to the 25, rather big numbers, right? So it starts off and just oscillates. What happens if we do the same time step, for instance, in this unconditionally stable mode? And that's this. What do you predict? What do you think? Based on the things we talked about. So we said that the conditionally stable one, the explicit one, has this oscillating behavior. It seemed that if we used a time step of 1 or 2 or of 5, it actually always ended up being ultimately going down to the right steady state value. So my guess is it will be close to the steady state value, which will be 0.5. See if I have to eat my words, but that's what I think it might be. So if we run it, we go back to the first time step. Yeah, okay. So it's going up from 0 to 0.5, so it's at 0.45, then it's at 0.4959, 0.4996, and then 5. And so it is. So the difference between unconditionally stable systems and those which are unconditionally stable is that if you choose the wrong time step, then you get a stupid result, an oscillating result which just goes unstable. At least with a unconditionally stable system, we could probably use as big a time step as we wanted. We'd still get a sane result. So if we used 1,000, we clean it off and we run it, what would we get? I think we'd get 0.5 all the way through. And it's there. 1,000 is 0.4995, that's 0.5. So it's still a sane result. But remember, be cautioned by the fact that what we talked about, discretization. And it's probably useful to revisit that. And I guess it was shown by this. And this whole idea of discretization. Unconditionally stable means that it will always give you a result that probably approaches a steady state, which it does in this thing after running it. Because after 1,000 seconds, it should really be a steady state. So it gravitates towards that. But the steady state result it gives, although it's kind of correct for the steady state, it's actually not correct for the time steps, because it actually would have reached steady state much before that, in many respects. And the other thing is that discretization, and so you can compare that to the conditionally stable one, which just oscillates and goes out of control. So those are two different behaviors. But don't, because it reaches some reasonable value close to the steady state, assume that necessarily it's right. It's not necessarily right because, one, the time discretization might not be fine enough. And so we might, and certainly for the one we just did, if we did, what we'd do, 1,000 seconds? Well, I guess at 1,000 seconds it was over here. 0, 1. It would be off this map. It would be over here somewhere. It was roughly 0.5. And so that would kind of be true, but we've missed out all the earlier stuff. If you use a more reasonable, smaller time step, then these results and these results can't both be right, right? So it has to be these ones at the finest time discretization that have to be correct. And so we'd want to be able to use that. But these also aren't correct for the real physical system that we might be interested in looking at. Because these are correct for this two-element system that has a kink in the pressure profile, but not for the true continuum system. And so we need to be aware of the fact that it matters what we do for discretization, both in space and time. An easy way to check it is to take your model, which has a physical attribute to it, has a shape and size and material properties, and you run the model for a given mesh with a given time step. You reduce the time step until you get to the same result at a reduced time step. And then you change the mesh and make it a finer mesh and see if you still get the same result. If you do, then you have a solution. You don't have to worry about it. And you physically solve this issue of being able to make sure that you're in this particular space here. It's good. That's fun. So good. So.